So to summarize everything, I have 16 questions for you to consider, 2 of which are trivial. So we'll go through and we'll try and spot those. Sometimes the order matters, sometimes it doesn't. Sometimes you're using some of the objects, sometimes you're using all of them. Sometimes the objects are all distinct and can be told apart, sometimes they aren't. And sometimes there's a condition and sometimes there is not. So the trick to this task, or counting theory in general, is being able to identify those 4 criteria for a question and then using those criteria to sort of model what your solution will look like. So this first one here, there are 5 bananas, 4 apples, and 3 pears in the fruit bowl. How many ways can 11 people each take 1 piece of fruit? So the first question is whether the order matters or not. So if you can imagine 11 people standing in front of you, one of them has a pear and one of them has an apple. If you switched the fruit in their hands so that the first one had the apple and the second one had the pear instead, would that be different? And I think so, because you have different people eating different types of fruit. To be a little grim, if one of them is allergic to apples, then one way it turns out okay, the other way it ends up in the hospital. Or if there's a worm in the pear, then that makes a difference. So, or if somebody just flat out doesn't like pears and they get stuck with one, that makes a difference too. So I think this is a question where the order matters. So the second question you need to ask yourself is whether we're using all of the pieces of fruit or not. So 5 bananas and 4 apples and 3 pears. 5 and 4 is 9 and 3 is 12. There are 12 pieces of fruit up there and only 11 people are taking them. So we're leaving one behind, which means we're not using all the objects. The next question is whether any of these objects are indistinguishable from one another. And I think for the purposes of what we're doing here, one banana and the next banana are essentially identical. So you can't tell the bananas apart, you can't tell the apples apart, you can't tell the pears apart, so there are indistinguishable objects. The last question, are there any conditions? It doesn't say anything special up there, just that 11 people are going to take a piece of fruit from the 12 in the bowl, so no conditions. One of the important things you're supposed to get out of this exercise is that when this happens to you, that when you're leaving some behind and there are indistinguishable objects, you must do cases. It's the only way to solve this problem. So as per the video on cases, I'm going to look at this and I need to reduce this into sub-problems. So the feature I'm going to pick on is the multiple objects. So I'm going to create a case where I have a banana left behind in the bowl, and I'm going to create a case where an apple gets left behind, and I'm going to create a case where a pear gets left behind, and that should be all of my options. So less 1 banana, less 1 apple, and less 1 pear. Alright, so if I'm going to do that, in this case, the less 1 banana case, instead of 5 bananas, there are only 4 of them. There are still 4 apples, and there are still 3 pears. In this case, there are 5 bananas, only 3 apples, but still 3 pears. In this case, there are still 5 bananas, there are 4 apples, and there are only 2 pairs. So when I go to work this out, there are 11 pieces of fruit in total, but I have 4 identical bananas, get rid of their shufflings, 4 identical apples, get rid of their shufflings, and 3 identical pears, I'm going to get rid of their shufflings. Let's see, 11 factorial. Is 399,16800. Four factorial is 24, and again 3 factorial is 6. So that monster number divided by 24 divided by 24 divided by 6 is 11,550. Now by the same structure for this one, 11 fruits to sort. There are 5 identical bananas, 3 identical apples, and 3 identical pears. So 399,16800. 5 factorial is 120. 3 factorial is 6, and again. So that monster number, 11 factorial divided by 120 divided by 6 divided by 6 is 9,240. And in my last case, sort all 11 pieces of fruit, 5 identical bananas, 4 identical apples, and 2 identical pears. So 11 factorial, 399,16800 divided by 120 divided by 24 divided by 2. 20 divided by 24 divided by 2. 6,930. And of course, in order to finish a cases question, if there are 11,550 ways to do it this way, and 9,240 ways to do it this way, and 6,930 ways to do it that way, then I will have to add them all up to get the total. So 6,930 plus 9,240 plus 1,1550 is 27,720. So there should be 27,720 different ways for those 11 people to select one piece of fruit from this particular arrangement of fruit in the bowl. Alright, I'm going to change this question a little bit. I'm going to change this question mark to a comma and append if Sheena must have a pair. So I haven't changed the fact that different people with different fruits makes a difference, so the order still matters. I still am only having 11 people choose from 12 fruits, so we're leaving some behind. The individual apples are indistinguishable, so that gets left behind. The only thing that's changed then is that there is a condition now that Sheena, for some reason, will have a temper tantrum if she doesn't get a pair. So I'm going to satisfy that condition first. Sheena gets a pair. Now, Now, that means that I'm not dealing with 11 people choosing a fruit anymore. I'm only dealing with 10 because Sheena got pushed her way to the front of the line, biting and clawing all the way, and got her pear and ran off into the sunset. So there's only 10 people left to shuffle. And that leaves only 2 pears left. Now, because I didn't change these 2 conditions, right, that we're still leaving some behind and some of them are indistinguishable, this is still a cases question. So I'm going to have to set up my cases. If there's a banana left behind, or there could be an apple left behind, I'm just going to write left. Or if there's a pear left behind. So if a banana gets left behind, I'm really only shuffling 4 bananas, 4 apples, and 2 pears, because Sheena absconded with the 3rd one. If an apple is left in the bowl, then I'm really only shuffling 5 bananas, 3 apples, and the 2 pears that Sheena did not steal. And if the pear is left in the bowl, then we're shuffling 5 bananas, 3 apples, and only 1 pear. So if we work that out, notice that 4 and 4 and 2, 5 and 3 and 2, 5 and 3 and 1, sorry, this should be 4 apples. That's why you double check. You notice that those all add up to 10 different people and 10 different fruits. So shuffling these 10 fruits that we chose to take, eliminate the shufflings of the bananas that are identical, the identical apples, and the identical pears. 10 factorial is 3628800. 62800. 4 factorial is 24, and again, and 2 factorial is 2, for a total of, divided by 24, divided by 24, divided by 2, it's 3,150. If an apple is left behind, I'm still shuffling 10 fruits, but I have to eliminate the identical bananas, the identical apples, the identical pears. 3628800. 5 factorial is 120. 3 factorial is 6. 2 factorial is 2. So 10 factorial divided by 120 divided by 6 divided by 2 is 2,520. And for my final category here, shuffle the 10 fruits that I take, eliminate identical bananas, eliminate identical apples, and I'm going to put the 1 in there just so that we see parallel structure. It doesn't really matter. And there's only 1 pair, so there are identical pairs, I guess. I'm just going to leave that in there. Doesn't change the answer. So 362,000. Nope, that's not right. Whatever that number is. 5 factorial is 120. 4 factorial is 24. And 1 factorial is 1. So 10 factorial divided by 120 divided by 24 divided by 1 is 1,260. And since I have a cases question, I could do it this way, or this way, or this way. So I have to add them all together. 1260 plus 2520 plus 3150 is 6,930. Just significantly fewer options than we had without the condition, which is encouraging. Condition questions should always have fewer options than a similar question without conditions. That should just make sense. All right. So, new question. 5 people are planning a party. How many ways can they help out if no one has specific roles? Okay, so if no one has specific roles, you're taking these people and you're putting them in a group, and it doesn't matter which order you choose them in because there isn't a president or a party chief or what have you. So this is a question where order doesn't matter. No order. Five people are planning a party. How many ways can you help out if no one has a specific role? So it implies that you're taking all 5. So use everything. And it's 5 people. People are always separate, independent objects. So it means that they are all distinguishable. So distinct objects. And it very specifically says no one has specific roles, so there are no conditions. Okay, now you may have already remembered that those are the particular choices for one of our trivial cases. If you think about that, 5 people are planning a party. How many ways can they help out if no one has specific roles? So that's 5 people doing all the jobs with equal responsibility and equal authority. Well, they just do it. The party happens. So those 5 people made it happen, and there's only one way that it could. They got together and they made it happen. So this is the trivial, one of the 2 trivial cases where there's no order. You're using everything, the objects can all be told apart, and there's no conditions. But if I were to modify this slightly, ways they can help out if I'm going to assign some specific roles. If 3 were in charge of decorations, and 2 are responsible for food. All right, so I haven't assigned a president of food or a secretary of decorations, so the individuals remain sort of unordered, but I've added a condition in here saying that I'm going to split them into 2 groups. So there are some roles, but they're categorical roles, not individual responsibilities. So still no order question. If you were to physically do this, go in and look at a group of 5 people, you're going to have to choose your decoration committee, choose the decorators, and then you're going to have to choose the food folk. Okay, so if you were to do that, you had 5 people available to you to choose your decorators from, and you have to take 3. And then once you've done that, there are only 2 people left to choose for your food committee, and you have to take all of the rest of them. And in order to arrange all these things, you have to choose your decorators and choose your food folk. So I'm going to have to do 5, choose 3. So 5 NCR 3 is 10. And 2 choose 2, there's only one way to do that. So the answer to my question would be 10 different ways. So the condition there rescued this trivial question and made it an actual thing that we could think about and count. So new question then. How many different ways can a family of 7 line up for a wedding picture? So as soon as you get a lining up question, that's obviously in order matters. Pop that in there, order matters. If I have 7 family members getting in this line, I'm using all 7. It doesn't say to leave anyone out. And 7 family members means 7 people, and people are always distinct objects. I keep writing G's instead of C's today. It's a Wednesday thing, sorry. And if I read that line of text there are no conditions. It doesn't say anything about where people have to stand, so no conditions. Alright, so a question where the order matters, you're using all the objects, none of them are indistinguishable, and there are no conditions. That's the basic permutations problem. So all I'm going to have to do is take these 7 people and I'm going to have to shuffle them. 7 factorial, which ends up being 7 factorial. It's 5040. Nice and straightforward. So in order to make this a conditions question, I'm going to take this sentence, erase the question mark, put in a comma, write the word if. The bride and groom must stand together. It is a wedding picture after all. And the 3 siblings must also be together. Now, just to be clear, the bride and groom don't count as the siblings. I intend them to be the siblings who are not the bride and groom. So this question no longer is a no conditions. This is a conditions problem because I've just spelled it out right there. So if I read this, that condition has separated my 7 family members into 3 categories. People who are bride and groom, people who are siblings, and everyone else. So if I were to group those people, there's sibling 1, sibling 2, sibling 3, the bride and groom, and then there are extras, for a total of 1, 2, 3, 4, 5, 6, 7 family members. Now, if you look at that, there's really only 4 objects to shuffle. So when I go to do the counting here, there are 4 objects that need to be arranged. This block, and this individual, and this individual. We can shuffle them all around. Within this block, the bride and the groom could be ordered themselves. So there's 2 objects there that need to be shuffled. And inside of this block, there are 3 siblings that need to be shuffled. So I'm going to shuffle them as well. And 4 factorial. 4 factorial is 24. 2 factorial is 2. And 3 factorial is 6. For a total of, 2 times 6, 288. Which is much less than the 5040 we had just a minute ago, which again is encouraging. because as soon as you attach a condition to a question, it should reduce the number of options that are available to you. So I have a bunch of sleeping bags in the closet. 5 of them are good enough to use down to negative 10 degrees Celsius. 3 are good to use to 2 degrees, and there are 2 that are only good to 8 degrees Celsius. So how many different ways could I throw 6 of them into my trunk? Well, by the time I drive off in my car, the order I place them in the trunk is irrelevant. So this is a no order question. There are 10 of them, and I'm only taking 6. So I'm only taking some of the objects. The only feature that's been described to me is their temperature threshold. So there are 5 that are indistinguishable here, 3 of these that are indistinguishable, and 2 of these that are indistinguishable. So I have some indistinguishable objects. Indistinguishable. And at this point, there are no conditions. All right, now, as with all questions, whenever this happens, that some of them are being used, only some of them are being used, and some of those objects are indistinguishable, you must do cases. All right, so the issue is that some of these, I'm not taking them all, and some of them are indistinguishable. So I'm going to build my cases based on the number of, I want to reduce it down so that I'm only selecting 6 sleeping bags. So my choices then are the negative 10 ones, the 2 degree ones, and the 8 degree ones. And I'm trying to pick 6. So if there are 5 10 degree ones available, I'm going to start with that one. I'm going to take all 5. I could take this one as my 6th and none of these, or I could take none of these and choose that as my 6th. Or I could only take 4 of these, 2 of these and none of those, or 4 of these, 1 of these and 1 of these, or 4 of these, none of these, and 2 of these. That all adds to 6. If I take 3 of the really cold ones, I could take 3 of my 2 degree ones, because there are 3 available, and take none here. Or I could do 3 and 2 and 1, or I could do 3 and 1 and 2, and I could try to do 3 and none and 3, but when I go to my closet, I notice that there are only 2 of this type of sleeping bag, so this won't work. I'm just going to erase it from my list. If I take 2 of the cold ones, I could take 3 of these, and I'd have to take 1 of those to add up to my 6. Or I could do 2 of these, 2 of these, and 2 of these. Or I could try 2 of these, 1 of these, and 3 of these. But again, I find out that there are only 2 available, so this one's going to have to go. As well as the next option, which would be 2 and none and 4, because I don't have enough. Or I could take 1 of these, 3 of these, and 2 of those. Well, that's 6 sleeping bags. And so I can't move another one down there because I don't have enough of the 8 degree sleeping bags, so that's finished. And if I try to take none of the cold ones, I only have 3 and 2 of the other type, which isn't enough for 6 people. So if I count up my cases, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 cases. Now normally within each case you would have to count them, but if you think about what's going on in this case here, this case says I have 6 objects, the order doesn't matter, and I'm taking all 6 of them. So as soon as that happens, that's a trivial question, because I've broken this case down so that I've said, all right, I'm going to reduce myself to 5 of the cold ones and 1 of the medium ones. And if I say that those are all the ones I'm taking, well, I have to take all of them. So there's only one way to do this. There's one way to do this. There's one way to do that. Now that I've broken them down, each of these cases is a trivial sub-question. So it's not just that there are 11 cases. In fact, there are only 11 ways. Now, if I were to change this to having a condition, I would erase this question mark, comma, and say, how many different ways can you throw 6 of them in your trunk if you must take 1 of each? So I've already got this table here of the all 11 cases where there were no conditions, and now I'm going to add this on here so that there is a condition. That should reduce my number of options. So I'm just going to comb through my cases and eliminate every one where I don't have 1 of each. So this case is no good because I didn't take 1 of those. This case is no good because I didn't take 1 of those. This case is no good because I didn't take 1 of those. This is empty. This is empty. And in all of the rest, I've taken at least 1 of each type. So there's only 1, 2, 3, 4, 5, 6 different ways. So if I happen to be shopping at the Giddy Goblin in Hanover, expect my endorsement check any day. If there are 12 new board games available for me to purchase there, and I've decided I'm going to take 6, how many different ways can I do that? Well, once I pick the board games up and take them to my house, they're going to go on the shelf, my kids are going to get a hold of them, and they're going to throw all the pieces around anyway. So the order in which I select them is irrelevant by the time they end up at my house. So the order doesn't matter. I'm not taking all of them, I'm only taking 6 of 12, so I'm only taking some of the objects. The 12 board games are all distinct, you can tell them all apart. I did it, I didn't use a G. And there are no conditions listed on this, so no conditions. So I shouldn't have to worry about cases because I have distinct objects here and there's no condition to generate cases. So if I were to try and count this, this is the standard combinations question. That there are 12 objects and I'm simply choosing 6 of them. So I'm going to need the NCR button. 12 NCR 6 is 924. So 924 different ways so that I can choose 6 of 12 board games. Now if I were going to make this a question with a condition, as always, I'm going to get rid of this question mark, put in a comma, say, if 4 of them are going to my house, how many different ways can I choose 6 to take home? If 4 of them will stay at the house, and 2 will go to the cottage. So that extra wording there has introduced a condition for me to worry about. So if I'm trying to count that, out of the 12 that are available to me, I'm going to have to choose 4 of them to go to my house. And of the ones that remain, so once I've taken 4 of 12, there are 8 of them left. Of the 8 that remain, I'm taking 2 to go to the cottage. So 12 choose 4, 12 NCR 4 is 495, and 8 choose 2 is 28. So 495 times 28 is 13,860. This is interesting because the last example had a smaller number. Turns out for this particular condition, if you think about it, because I'm putting them in 2 locations, that has increased the number of ways I can shuffle these things. So I've put a little bit of order back into this question with this condition. And you notice in all of these questions, the ordering questions have much higher numbers of options. So introducing the order in here has increased my choices. So there are 4 cowboy hats, 3 ball caps, and 2 top hats in the closet. How many different ways can 9 people choose a hat? I'm going to add into this question, there are 4 identical cowboy hats, 3 identical ball caps, and 2 identical top hats. So if I were to go through this, I have 9 people that are going to put these on, and even though that word is in there, choose, this is an ordering question, because 9 different people putting on these different hats, you can tell the difference between me in a top hat and me in a ball cap. So this is a question where order matters. See, 4 and 3 is 7, and 2 is 9 hats. So 9 hats for 9 people. We're using all of the objects. But because I, after the fact, tossed that word identical in there for each category of hats, some of these are indistinguishable. And if I read the text, nothing up there says there's a condition, so this is a no conditions problem at the moment. And you'll notice in this list, I don't have to generate cases because I am using all of the objects, despite some of them being indistinguishable. So this is the type of problem where we have to shuffle them and then eliminate the arrangements of similar objects, or things you can't tell apart. So there are 9 hats, shuffle all 9. Once you're finished shuffling all 9, I have to eliminate the arrangements of the identical cowboy hats, the arrangements of the identical ball caps, and the arrangements of the identical top hats. So 9 factorial is 362,880. Four factorial is 24, 3 factorial is 6, and 2 factorial is 2. for a grand total of, divide by 24, divide by 6, divide by 2, it's 1,260. All right, pretty straightforward question. So if I were going to modify this so that there were a condition all of a sudden, how many different ways can 9 people choose a hat if Casey will not wear a ball cap? Okay, so this is now a question with a condition. And if you think about that, if Casey won't wear a ball cap, then he either is wearing a cowboy hat or he is wearing a top hat. So that's going to generate our two cases, or it's going to generate two cases, and sometimes conditions make case questions. So Casey in ball cap and Casey in top hat under that first set of conditions. If Casey's in a ball cap, then instead of shuffling 9 people, I'm only shuffling 8 hats and people, and one of the ball caps is no longer available, so there's only 2 ball caps. Under these conditions, Casey in a top hat, I'm still only shuffling 8 hats because he's already run off with the top hat. And instead of 2 top hats available, there's only 1. So to do the counting for this, 8 hats, shuffle them all around, and eliminate the repeated cowboy hats, the repeated ball caps, which there are only 2 now, and the repeated top hats. So 8 factorial is 40,320. 4 factorial is 24. 2 factorial is 2. 2 factorial is 2 for a grand total of 420. For this one, Casey in a top hat, there are still 8 hats to shuffle. There are still 4 identical cowboy hats. There are 3 identical baseball caps. And there's only 1 top hat. Now again, I could have left that one out because 1 top hat is not really multiple indistinguishable objects, but I'm just going to leave it in there for parallel structure, so just so they look the same. 8 factorial is 40,320. 4 factorial is 24. 3 factorial is 6, and 1 factorial is 1. So 4320 divided by 24 divided by 6 equals 280. And since you can do it this way or this way, I'm going to have to add them together. 280 plus 420, that's not right, 420 plus 280 is 700 different ways. So if there are 4 tomatoes and 3 cloves of garlic on the counter and you're making tomato sauce, how many different sauces will you end up with if you throw everything in the blender? Well, if you are familiar with how blenders work, it doesn't matter what order you put them in, it all comes out as slop on the other side. So the order doesn't matter here. I'm using all of the objects. Tomatoes are tomatoes, garlics are garlics, so you can't tell them apart. And there are no conditions. So these two things together, the fact that there's no order, that the order isn't important, and that I am using all of the objects, that has rendered a trivial case. So, and if you think about that, there's 4 tomatoes and 3 cloves of garlic, and you toss them in the blender, well, that's it. You have a bunch of stuff in a blender. And there's no more ways to make that more interesting. So we've generated the trivial question here. The answer is just 1. But if I were to toss in a condition to try and rescue this and make it more interesting, how many different sauces come out if you have 2 different blenders? If you are using 2 blenders, comma, one of which can only hold 2 ingredients. So it's one of those teeny tiny ones, like a magic bullet. Again, waiting for my endorsement check any minute now. So if I were to do that, I'm going to have to pick the 2 ingredients that go into my magic bullet. So into the small one, I'm either going to put in a tomato and a tomato, so that in the big one, the big blender, the rest go in there. Or I could pick a tomato and a clove of garlic and the rest over in the big one. Or I could put 2 garlics in my magic bullet and the rest over here. So those conditions have generated 3 cases, so I go to count them, and I'm back to having to take all of these objects, which is a trivial case. So if I have to take all of the tomatoes I set out for myself to shove into the small blender, there's only one way to do this. There's one way to do this, one way to do this, one way to do this, for 3 ways, 3 different sauces in total. So when it's course selection time, presumably you already did this back in grade 11 before you started grade 12. There are 14 4U level courses being offered. How many different ways can you rank your top 8? So that word there, ranking, doesn't mean pick them. It means actually put them in order, right? This is my first choice. This is my second choice. So that the people in guidance know which ones your priorities are. So if you're ranking them, then the order does matter. If you're only taking 8 of 14, then you're only using some of them. Those 14 4U level courses are all distinct. You can tell them all apart. One assumes that you wouldn't confuse English with chemistry. I suppose if you're going to nap your way through both, then it doesn't matter, but don't do that. And if I read through the text, I don't see any conditions at all. So we have the classic problem where the order matters and we're just eliminating the arrangements of the ones we don't use. So if I go up here, there are 14 courses I'm going to have to shuffle. Out of those 14, I'm only taking 8. which means I leave 6 behind. So I have to eliminate the shufflings of the 6 I leave behind. 14 factorial. Well, that was neat. 14 factorial is a really big number. 8.7178291 times 10 to the 10. And 6 factorial is 720. So if I type that in directly, 14 factorial divided by 720 gives me 121,080,960. 121,080,960 different ways. So, with that little piece of information in mind, the next time you're at school, you should socially distance hug your guidance counselor because they've had to sort a huge number of people's course selections in order to provide you the timetable that you have now. So if I were to change this so that there was a condition, I'm going to add in the fact that, comma, if English, that's ENG for you, must be in your top 6. Okay, so that condition has generated some cases. So if there are 6 slots in your timetable, 2, 3, 4, 5, 6, perhaps you chose to put English as number 1. If you did that, then there are 13 choices for number 2, then 12, then 11, then 10, then 9. So that is 13 factorial, 13 courses other than English to shuffle, and you are leaving 8 of them behind. Is that right? Yes, because you only have to choose 5 more out of 13, which means you're leaving 8 of them behind. Now, I could draw this out a number of times, sliding English down the pile, but the next one, if I do that, just looks like this. And instead of the 13 here, it goes up there. 13 choices for number 1, 12 choices for number 3, etc. So I could have that English first, or second, or third, or fourth, or fifth, or sixth, which means there are 6 different ways I could slot that E for English into my top 6 picks. So if I were to count this out then, 13 factorial, here, 13 factorial is 62270200800. 8 factorial is 40,320 times 6. Then 13 factorial divided by 8 factorial is 150,440 times 6 is 926,640. So that concludes our trip through all of the permutations and combinations questions. So if you think about this in an ordered counting kind of way, you have choices between ordered or not ordered, all or some, distinct or indistinguishable, conditions or not. So that's 2 times 2 times 2 times 2, which is 16 possible questions, 2 of which are trivial, for a total of 14 questions that are actually worth your time and energy. So when you're staring at a test or the practice problems or just life in general and you're trying to do a counting problem, it turns out there are only 14 different counting problems. And we've been through all of them now. So any question you come across must fit one of these models. So if you come across something where the order doesn't matter, you're leaving some things behind, you can't tell them all apart, and there's a condition, well, that's one of the 14 problems we just walked through here. So if you can get good at answering these 4 questions and identifying which type of problem it is, then counting theory becomes a reasonably straightforward exercise. So when you go back to this sheet, so you think you know how to count questions, keep that in mind. You should be asking yourself these 4 questions. And in fact, I would like you to write this down, the answer to these 4 questions, for every problem you try. Because when I go to mark them, if I can see that you properly identified which category it was, but then something went wrong here, I know that it's a mechanical error and not a thinking error. So if you could please kindly provide me with this information, then I can see your thought process. And if you write this information down and you're not sure how to do a question, sometimes writing this out will trigger your memory for which type of problem it is. So good luck, because this is the last task in data management.